Hello, it's Greg Allison with Greenest and Galactic Greg. It's come to you on the 23rd of February, 2021. Time on deck is 23:4600 hours Central Standard Time. Yes, it is almost the 24th and will be long before I finish this video. And I'll post this video somewhere later in the day because I just don't deal with the dog for posting this late. Now, all right, what are we talking about? Last video, I talked about the Laschamps Excursion, 42,000 years ago, which caused climatic havoc and apparently wiped out a lot of megafauna and Neanderthal man. Caused Cro-Magnon ancestors to use red ochre and live in caves to stay away from the UV and the cold and all the other stuff going around at the time. But the question comes, what is it that causes the cold weather of the Laschamps Excursion? What is it that causes cold weather? Why does it get cold when the magnetic field drops in intensity so much? Now, as it occurs, you know, some of the articles are just talking about, well, that just also happened. It's just coincidentally these two big out of the ordinary six signal events just happened to happen at the same time. Do you think maybe one might have been the cause of the other? Just possibly? We're going to entertain that idea because, indeed, I think there's something to look for there. So let's go looking in a minute. Now, before we do, bear in mind, what do you do when it gets so crazy cold, when UV is so high? You know, the things you got to do to protect yourself. You know, you need to, for yourself, grow indoors because the crops outdoors, the big agriculture is going to be failing. This is the time to learn how to grow your own garden. And right now, the seeds are a real good deal to buy because you can still get them. There's a lot more people gardening now, so the demand for seeds are going up. And the primary gardener seed buying time is February, like early February. We're on the late end of it. So I would say get your seeds while the getting's good. Go to True Leaf Market. They got all kind of seeds and links below, including microgreen seeds, which I do videos on this channel to show you how, on Greenest, to show you how to grow them indoors. Some of my older videos cover that in a fair bit of detail, and I'll do some more of that in the not too distant future. How you can grow lots of food indoors and only need sunlight for a few hours. So, you know, if you have a power system problems, you can rotate them around through your windows, and that'll be enough sunlight to get them going. That said, you can also hey, you know, you might have to grow in a cave. You might have to throw some compost, worm castings, and some mushrooms in there, and bing, bing, bang, bang. Hey, get things growing that way. Worms, worm castings. There's a lot of stuff you can do when it's hard to do. And I'll show you a little bit of a snippets of my universal habitat concept where we can grow indoors, grow year round, and produce enough food to feed your family. All right. We'll do that toward the end of this video and some other things because I showed a little bit of that earlier. But also do bear in mind, go to prepwithgreg.com, 20% off 2 of these for a week or 1 for 2 weeks. A little bit cheaper per serving if you buy the 2-week deal. A little better than 20%, a little less than 20% on the 2-week. 4 week, 2 week. 2 of them is 4 weeks. And you get 2,000 calories per day, breakfast, lunch, and dinner. You get this deal and you'll be a winner because it's only about $8.10 or 11 cents per day, depending on which way you go. All that said, go to prepwithgreg.com for that. Now, let's get into this. We're going to talk about what's happening here, what's happened. Let's go screen share. We're going to go to a whole slurry of articles here and just boom, right through them. La, 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 la. Well, let's start here. How about this? When Earth's magnetic field flipped 42,000 years ago, the climate changed too. Holy smoke. How do you come up with that? You tell me. I tell you. The Adams event. The Adams event. Family. Yeah, it's different Adams. This is the guy that Hitchhiker's Guide to the Galaxy. I said universe in my last video. I meant galaxy. I am Galactic Greg's too, you know. I should have got that. Anyway. So I'm not going to read this article. I'm just going to show you that they talk about in here that when the poles did a temporary excursion, about 1,000-year little mini pole flip, that the level got down to maybe 5%. Radioactive carbon-14 levels went up in the atmosphere. And yeah. Let's see. There's one more thing I was wanting to show you. I'm talking about ice core samples, grand solar minimum coincided. Why? So it says Earth's magnetic field was lost and there was a prolonged period of low solar activity, which would further reduce Earth's protection. Well, was it really a low sun activity, or did it just look like a low sun activity because you had less heat? Are they inferring that? How do they get there? We're going to go into how a low magnetic field would make it look like you had a low solar influx. It could just been the sun was getting blocked by cloud nucleation. Maybe that's what was going on. And there may be different mechanisms to, or more than one, to cloud nucleation. So we're actually going to go into an article over here, which is kind of negative on the cloud nucleation story, at least in terms of the classical sense of it. But in the end, it's not conclusive. So we'll go into this stuff a little bit. So let's go over here. Laschamps event. I'll see what they show you about the Laschamps event. Geomagnetic field was at low levels, 42,200 to 41,500 years ago. Okay, see, it dropped to only 5% of the current strength during this transition. Excuse me, friends. But what else happened? This reduction in geomagnetic field strength, they said the reduction in the geomagnetic field strength resulted in more cosmic rays reaching the Earth. The reduction in geomagnetic field strength resulted in more cosmic rays reaching the Earth. Now, we've talked about these cosmic rays, causing greater production of cosmogenic isotopes, beryllium 10 and carbon 14. These are typically seen as solar activity proxies, but in this case, we're getting this solar activity proxy as a result of the magnetic field dropping. Now, some people paint them like they're just correlated with each other, but the grand solar minimum did not have the same kind of, the modern minimum did not have the same kind of drop in magnetic field strength that we know of. So, at least I'm not knowing of that. So, I wouldn't submit that the two are directly correlated, but the drop in the magnetic field can induce an influx of more cosmic rays, as would a drop in the solar field. And if you get both going on at the same time, a true grand solar minimum, and this drop in the magnetic field coincident, what some people think we're coming into, then bada bing, bada bang, you might be in for a rough ride. Some people think that's where we're heading. All right, let's look at these Vostok ice core samples. These Vostok ice core samples go back over 450,000 years, my friends. 450,000 years of ice core data taken from the Vostok station in Antarctica. There's also Greenland samples too. So these two correlate. Now, the width of this little hourglass here is about 10 to 12,000 years in the cycle, about 10,000. So if you go down through what you see here is several periods of glaciation. Glaciers, 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 with these little warm periods up here. Sometimes the warm periods were brief. Bing, bing, bing. That wasn't so brief. And then there's this one. And just so happens, this is where we're at today, is right here at the end of this one here. Notice, they tell us, they keep telling us, oh, it's never been this warm. It's so warm now. It's never been this warm in blah, 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 recent history, or sometimes they'll tell you since the warming in 50 million years ago. They claim that's where we're going. Well, it was warmer here. That's warmer here. Actually, that is warmer than here, except for that one little peak way back here. It's much warmer here. This don't even go back to the 50 million years. It was warmer here. 1, 2, 3. Every one of these were warmer, although they were briefer and they dropped off there. That one was wider, but it starts dropping off pretty good. But look, it was all the way down to here that long before it got down to our level. Pretty, not dissimilar from where we're at. That level a little bit. Well, that is where we're at, isn't it? Pretty much. Oh man, that whole area here was warmer than we are today. Okay. But notice there is a periodicity of sorts here, and it goes back, this whole quaternary glaciation period is 2.58 million years. And this is what occurred through the entire 2.58 million years, with these peaks originally being 41,000 years apart. And over time, they're stretching out. Now you can see these are about the same, but these are longer than that, and this one is longer than that. Here's a couple other funny things in here. Look at these twin peaks. Look at these twin peaks. Look at these little peaks and these little peaks. See, there's, boy, if this is not repeating itself, it sure does rhyme. Twin peaks, a little bit of a twin peak. Maybe something similar here too. Look at that. Look at that. Very similar. So it just keeps getting longer and longer. Now there's a special reason for this extra longness here. This period right here, this is the Younger Dryas. And it got brutal cold here. I mean, this was cold. The only time it rivaled it was just right here briefly. But look how fast that warmed up. Brief cold and boom. Some people think because plants haven't grown while it's so cold down here to CO2 levels spike. The spike in CO2 levels lead back to this. That's what some people think. But there's another thing that I find interesting, or several things I find interesting. Look down here. This is dust concentrations. Dust concentrations. Notice in the coldest periods, right here to here, here to here, here to here, that to that, this to this, this to this, yeah, that to that, like directly correlating. Boom, 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 boom. Dust. Where does dust come from? Well, we believe there was an impact here. The impact could have kicked a lot of dust in the atmosphere, but there was already something happening here, building up something. And we're going to show you this period also. And we're going to show you there's just a lot going on here with the climate, my friends. This is not exactly a one-to-one with the Milankovitch cycles. I mean, that could be a driver. We're going to talk about drivers. But what was this dust? There may have been multiple causes. Some of this may have been volcanic, or it may have been, this may be all impact driven. It may be that the flux density of stuff coming in our solar system and causing impacts has a periodicity to it. And this is, but it's not a regular periodicity. The periodicity increasing over time is not like an orbit or a circle periodicity. It's more like a spiral. It's spiraling out. Isn't that interesting? It was tighter. It's getting longer and longer. And these peaks are getting lower and lower. Now this glaciation period here was not as cold overall as this one until the very end. But that one got a little bit colder at the very, very end. But overall, if you take the average, except it was longer. Now that was a warmer period than this one. And this one don't seem to near as bad as this one or this one in terms of the depth of glaciation period coldness. But this is cold. This is degree C, guys. Degree C is cold, cold, cold. This is zero right here. Okay. I guess that's the average. This must be a difference from the baseline, whatever they consider the baseline. But I don't think it's actually the freezing point. I hope not. But you drop in here, things are freezing. It may be the freezing point. We kind of go in and out. Wow, guys. Carbon dioxide. Carbon dioxide. Oh, carbon dioxide's never been higher. It's higher here. About as high here. Much higher here. What? Much higher here. Those ancient mammals would have all too much fun in their jet planes. Much higher here. We're told that this level is going to cause mass extinction. We're told that I just saw in an article said baby sharks were not going to survive because oceans were getting too warm. Yeah, that was an article that came out later. All this junk they put everything they can to scare people. That is trash. It's garbage. Sharks survived that 50 million year ago warming period because sharks predate that. Sharks were here around in the Triassic period. No, the Cretaceous period. Excuse me. I'll show you the Cretaceous period. The sharks were here. And I know there's a shark tooth in the roof of Cathedral Caverns near Grand, Alabama. Bingo, that goes way back in time. So let's go back and look at some of this stuff. Okay, my friends. Now, we're looking at this period right here, from here to here and over here, okay? Boom. Look at this. Here was the Ice Age, you know, the Pleistocene. There's some kind of event here, Heinrich event. There's all these events keep on. And there's this boiling Autorod. Boiling Autorod. They thought we were coming out of the Ice Age here. If we had of, it might have had it much more similar to the previous cycle in length. You see, if it might have been like here to here, you know, right about here, we start to come out of it, and then boom, down we go again. At least that's what they were thinking. We were coming out, they thought. Yeah, they didn't come all the way up here on this chart. So it wasn't quite as warm in Greenland, but then it got Greenland. So, and then down and boom to the bottom. And dust up, CO2 falling to dust because nothing growing and everything's dusty and cold. What's all the dust? Is the dust because of the cold? Does the dust make the cold? Good question. Is the dust just from all the plants that died out? Or is it from volcanoes and impacts? You tell me, but that dust is most interesting. So back in here, bang, we know there was an impact. You know, this is thought becoming, it was cooling. Look, very significant cooling trend. I mean, it would have taken you down to here. And then boom, straight down. This is the Younger Dryas event right here. There's some attempt to recovery. It's tough to come out of that. Then all at once we came out of it. I guess because that's another little dip. They cover all this as the Younger Dryas period. But that's a major recovery. This is when ice start, yeah, here ice was starting to melt, ice reformed. Ice starts to melt, yeah. And then maybe it starts to reform a little bit, and then we're coming out. And then like 2,000 years ago, we had a cold event. What was that? This is where we're at today, guys, with all this great warming we're having. This is the modern minimum. Got cold here. Glaciers advanced right here. Doesn't take you much difference in temperature for glaciers to start advancing or retreating. We're going to show you that too. This is a late medieval warm period. You see this about 1,000 years ago when the Vikings were all over North America and Greenland, and this was called Vinland. Just a little bit higher than here. A lot higher. Yeah, actually a lot higher than where we're at, but not as high as it was back here during the age of the Phoenicians and Greeks. And then look here, warmer here. And then we had, you know, some cold, 5,000 years ago. A cold spot right there, real good one. About the time of Noah's flood, right? In legend, in the Bible. I shouldn't say in legend. And then warmer prior to that, warm, cold, like modern minimum. Well, that modern minimum is colder than that, though. Actually, that's warmer than we are today. Holy smoke. There's a general trend line going down here, especially right here. Look, definitely a trend. And look at that. It's warmer than that. Got more area under the curve, too. All this period, if you draw straight up, line straight out, is warmer than we are today. But it's so warm today. We're glad to cook everything. Oh, well, that's what they tell you. They tell you that every day in the news, every day, every article, every newscast, everything comes out. Constant. Mind control. Boom. Listen. Watch the birdie. Listen. Watch the birdie. Listen. Watch the birdie. Listen. Watch the birdie. This is the truth. This is the truth. This is the truth. This is the truth. That's the hogwash. Yeah, it's the hogwash. Okay. All right. Hey, this is the science. They tell you, why are we not watching science? Bull, 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 bull. 90% of all scientists absolutely agree with them that fund them. Yeah, this balling Autorod event was pretty interesting. An abrupt, warm, and moist interstatal. So it was like an interstatal, interglacial in the glaciation period. But then it started dying off real fast, brief, moist. So it's thought the glaciations tend to be somewhat dry because there's not as much stuff in the atmosphere. And here they blame the warming on increased water temperatures in the North Atlantic, possibly triggered by strengthening of the Atlantic meridional overturning circulation. A lot of things in our climate are dependent on this cycle right here. So that's another cycle. Bing. Okay. This article here is a bit critical on the notion of the Svensmark cloud nucleation. But it don't rule it out. Cloud nucleation is a result of cosmic rays. It's just saying that the current models are not quite sufficient. Although, some had refuted the whole idea. So, oh, it don't work. You don't get cloud nucleation from cosmic rays. When I first started talking about that, a lot of people who were on the side of global warming were really beating on me with that. Oh, it don't. Actually, this says it does, but it just says it's not significant enough. Still kind of favors them in general, but they really can't rule out cosmic rays as causing more clouds through other mechanisms. So what we're talking about here, what we typically discussed here, is the causal agent being galactic cosmic rays, GCR, galactic cosmic rays. And so what we talk about is cloud condensation nuclei, cloud condensation nuclei, CCN. That's the two most used acronyms here. Excuse me. Cloud condensation nuclei. So what they said here basically was a lot of studies earlier, but the data was bad. They had chambers they might try to test it with. This is Svensmark in 2000, who said, hey, we got this cloud galactic cosmic rays. It must be causing the stuff, because what they found was there was a correlation with grand solar minimums and solar minimums in general and cooling. So what could the answer be? Some people say, why don't exist? There's no correlation. Well, that correlation is what drove them to looking for this data. And Svensmark, thought these, and Fritz Christensen thought they found some answers to this with the galactic cosmic rays, which are increasing at this time frame. I guess like galactic cosmic rays increased, excuse me, 42,000 years ago. And they got cool then too. Oh yeah, I didn't show you that, did I? Let's go back to the Vostok, show you where that is, if my system will let me get there. Vostok. Let's go back. 42,000 years ago is this dip right here. You see that dip? It's a sharp, sudden dip, that real narrow, about 1 pixel width all the way down, which is about 1,000 years. But you see, it was quite a dramatic departure from where it was. I mean, this whole period here is colder and it gets warmer. Colder, 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 and it warms up. This being the average of this period right in here, but this drifts way down. Of course, this was a huge die-off over here. This was a megafauna die-off. This was a bigger megafauna die-off. This got a lot of the creatures in Australia. This took a lot of the creatures in North America and Europe, a lot of the big megafauna. So megafauna worldwide suffered here, including Neanderthal, man. This apparently got to Neanderthal. Coldest it had been prior to this was all the way back here. Quite a few thousand years earlier. It was about 40, 50,000, about 40,000. So that's a lot of time in the life of critters, 40,000 years. Longer than we've been up here. All right, maybe that's it. Let's go back over here. So what they claim in here is that these particles do indeed, that the galactic cosmic rays do indeed cause initially particles of 1 nanometer to form and start growing, a little bit of a nucleation. The small ions may increase the nucleation rates and may the formation rate of 1 nanometer aerosol particles. We're not going to go on to this, but they claim they got to grow to about 50 to 100 nanometers and actually to form this CCN. And again, CCN is cloud condensation nuclei. Nuclei that will actually form clouds. A bit bigger, according to this. So they got to be stable to get to that point. And some do, but they're claiming it's just not quite enough to cause climate change. This graph here shows the ionization in the atmosphere, where you got sulfur acid vapors and low volatility organics. Yeah, organics play a big role in this. whole process of the cloud nucleation. We're not going to go all in that's more technical. I want to get for the points of this discussion, the amides and everything else that form. We will skip that part of this discussion unless we want to be in there all night long. So suffice it to say, I talk about various other studies that play at this. And let's see, I need to find some keywords in here. Give me a second here. The cosmics leaving outdoor droplets. So yeah, this whole thing is about this study here. The cosmics leaving outdoor droplets, or cloud. Nice acronym for stuff that would cause cloud nucleation, right? Was conceived by Jasper Kirby of CERN in the 90s. And so previous labs were not able to get enough purity to have good test results. Well, they can't claim they got absolute purity in here either. And in fact, they make that case, but they just claim it was better. So, however, until recently, there has been considerable uncertainty involving which vapor species participate. Additionally, theoretical calculations of nucleation rates were often incorrect by orders of magnitude. That's, each order of magnitude is a 10. Orders is more than 1 10. That's like two orders, hundreds, 3,000s or more. He's saying they're way off. This is, data, a lot of the data that was refuting this other stuff, including that. So, including guys that refuted Svensson. So, let's see here. Cloud measurements, parameterization. Recent work done outside the cloud group has also demonstrated the importance of these diamides. We're not going into that. I'm looking for something here because there's talk about how they estimated things in here. They model and estimate. The cloud team applied their experimental results. Now, their experimental setup, they don't say it was 100% purity in there. There are still contaminants. They can't get all the contaminants out of the lab, but it was better than the previous ones. That's all they're saying. It's better than the previous one. Applied their experimental results to global aerosol models to evaluate these models. And where I work at, we say all models are bad. Occasionally, sometimes some models are useful. So yeah, we're real negative where I work at on models. The cloud team has used experimental results, applied their experimental results to global aerosol models. So they're having to use modeling along with their experiments. Their experiments give them a narrow spectrum of findings. Now they're trying to apply that to the bigger models. The models are mathematical assumptions on how we think the universe operates. Well, we never quite get there. Reality is always includes variables that we miss from time to time, sometimes a lot, maybe driving functions even. Talking about the importance of I'm hunting some. So they're looking at the difference between pre-industrial and post-industrial. They're thinking that makes a big difference, especially since the organics and the aerosols matter. Now we're getting more down to it here. Let's see. Talking about their clear sky hypothesis. The study uses global aerosol chemistry model to estimate. This study uses a global aerosol chemistry model to estimate. So look at model and estimate. We make an estimation based on a model. Okay. Now, what they say is, well, this also fits with earlier models and estimates that other people have made. There's some of these that this still agrees with. And then in the end, what they're saying here is this. They find some damping in responses. Going out this way on the chart is an increase in galactic cosmic ray flux. Going up this way is the nucleation that occurs, a small 1 nanometer particles. And down here is the CCN, where you get in cloud nucleation, which is a little harder to do. They say this is damped because this is a straight line that starts falling off. So they say it's damped. This is a difference between a solar maximum and a solar minimum. So if it were linear, this would be going way up. It's going up, but not as much. So it's harder to get from here to here because the particles got to grow more. They said this being damped here amplifies the damping here, and so you still get some growth, but it's very, they think, not enough to cause the climate change. That's what they think. But they don't rule out everything. Does this cloud find in close the door on any possible galactic cosmic ray cloud climate connection? No. Other work has suggested that cosmic rays could influence the freezing of liquid water to ice and clouds. Ta-da! Ice crystals up high, same effect. Or may influence the amount of condensable material, Svenswork 2013, and other possible mechanisms might exist. So they're suggesting there's several other mechanisms which could get you to the point of having cooling or cloud nucleation or other effects that block sunlight when you have higher fluxes of galactic cosmic rays. So they got an interesting experiment. They just study a lot of stuff, but it's still experimental. They still are using experiments that are somewhat less than perfect, but pretty good to make apply to models to make estimates. But what they're claiming is what's damping the specific numbers don't really matter because you still got damping. They discovered a phenomenology and everything seems to say this is true. But what they're saying down here is there's other mechanisms. Because, guys, what we're finding, Laschamps, magnetic field goes down, cosmic rays go up, temperatures go down. Grand solar minimum, temperatures go down, cosmic rays go up. Solar minimum, cosmic rays go up, temperatures go down. Wow, anytime cosmic rays are going up, the temperatures are going down. So that's interesting. So, you hear people bat this stuff all around, all over the place. So there you go. That's the story. So if anybody wants to shoot it out, well, we got this study that shows that's not the case. Say, well, no, you can't rule it out. You can't rule it out. And this is the scientific papers or an article. That's not the scientific paper. This is an article about it from JGR Atmospherics. Okay. This is the Advancing Earth and Science publication here. But here's what a lot of people don't know. A lot of people don't know. Remember this week, we're back over here, this little Maunder minimum. Would you believe ice advanced during the Maunder minimum? Would you believe that? Would you believe that ice glaciers advanced here? Glaciers probably advanced here. Glaciers advanced here. Melted here. Advanced, melted. Advanced, melted. Advanced, even from here to here, advance and melt. Advance and melt. Imagine that. Well, here we go. We're about to go into that. Not a lot of people know that. Look at this, guys. Glacial advance during the Little Ice Age. The history of glacial advance in the European Alps is well documented. Historian Brian Fagan offers this horrifying account. They're talking about the 16th century, how there was poverty along the lines where the glaciers were taking place. 1579, a visitor described the village as a place covered with glaciers. Often the fields were entirely swept away. Fields were entirely swept away, and the wheat blown into the woods and into the glaciers. Now, the glaciers were making rapid advances on villages back during a couple of periods in the past, including the here we are in the 1600s, and again during the 1800s. 1627 to 1633, this community here lost a third of its land through avalanche of snow, glaciers, and flooding. Pardon me. But the Little Ice Age was not only restricted to Europe. Icelandic glaciers reached their Holocene maximum during this period. Iceland was heavily glaciated during the last glacial maximum. It talks about all this glacial melt we have today. Well, it's melted from this period here. This was the biggest glaciation during our current interglacial period. across Greenland. Not only have the history of the Viking colonies, the Middle Ages, we also have ice core data showing temperatures of Greenland were about 1.5 degrees C warmer 1,000 years ago than now. And also this period of 1875, the lowest point of the Little Ice Age, marked the coldest in the last 10,000 years in Greenland. Meanwhile, analysis of the moraines showed the Greenland ice sheet may have receded tens of kilometers within the present-day margins during this early mid-Holocene before reaching their maximum early in the early Holocene during the little ice age, a maximum then, back in the 1800s. See, same things talking about here in Alaska. So this goes on and on. The data allow us to infer the maximum advance of the Cyprus Glacier in Chile. You may have heard Al Gore talk about that. Attributable to the Little Ice Age, occurred around 1842, maximum advance. The first historical retreat was recorded in 1858. You know, we saw pictures of valleys full of glaciers, and now they're not. These records began in AD 1675 with typical conditions probably similar to those at present prevail. And it talks about these ice growing while it's snowing. But glaciers can actually seem to form and move pretty quickly. Oops. Did I stop the share? Didn't mean to. Here we are. So, no record of, yeah, quite a bit. So there's quite a bit there, but guys, here we are. Let me show you something. We are in the Quaternary glaciation. Started 2.58 million years ago. And is ongoing. Yes, we're still in an ice age. We're in an interglacial period of an ice age. Okay, friends, look at this. We're in interglacial right here. And see this cap? Yeah, it's been warmer in the past, okay? In fact, this is what the maximum extent of the ice typically looks like. We know it's actually gone in here more in the past. It's kind of interesting to get this warm area in parts of Siberia and Alaska, right? So, so what it says is, although geologists describe the entire period as an ice age, in popular culture, the term ice age usually is associated with the most recent glacial period during the Pleistocene. And it also goes in how we've had many other ice ages in the past. So there's those Vostok ice cores I just showed you a minute ago. Here's other causes: precession, obliquity in an orbit, eccentricity in an orbit, solar forcing, and stages of glaciation. See there, look here. There are various other frequencies of Earth's precession. Look at that. That's like amplitude modulated signal in AM. So, you know, there's many forcing functions in here. Solar forcing, eccentricity in the orbit, obliquity in the orbit, precession of the Earth itself. So, but look at this. Do these actually match? I don't know. That's peak periods, that's warm. This is peak, and that might be peak there, but look, that's peak, there's no minimum there. See, I don't know. That's how this really matches. If you add these up in some kind of a summation, you might find something there. Now look at this, guys. We always talk about, oh my God, the world's going to end because our CO2 is so high. We're getting up close to 400 parts per million. It's the end of the world, 400 parts per million. So in this article, look here. Dip in carbon dioxide may have helped the dinosaurs walk from Brazil to Greenland. Oh, dip. What, from 400 to 300 parts per million? Well, the dip was 4,000 parts per million to 2,000 parts per million. All right, so in the Triassic period, Earth had 10 times more CO2 in the atmosphere today. Not one time, not 1.5 times, not 2 times, not 3 times, 10 times. And in fact, it dropped dramatically to a point that was only 5 times as much. Wow. So this article is really thinking that at this point in time, there's so much rain, it's just difficult for these large creatures to be crossing rivers, raging rivers, and that the polar regions were drier at the time. And when it dropped down, because it was drier in the polar regions, and the jungles were something else in the tropics where the dinosaurs were at. And there was just so much stuff from the munch on. Maybe they couldn't even get their way through the trees hardly. It all changed a little bit. They found their ways up. They found their way up to Greenland. And they chomped around in Greenland for some time. It took them a whole age from the Triassic to the Jurassic. The Triassic to the Jurassic they get from South America to Greenland. And what they're saying here is if they only walked a mile a day, they could have covered that ground in 20 years. Somewhere it says that here. I've read this stuff. So we're talking about going from South America, right here, to Greenland up here. Looks like they had to swim a little bit. Of course, the continents looked a little different then. So you can do that in 20 years. So guys, if you start hiking now, you could be down in Argentina. Yeah, in less than 20 years if you come from around here. That's about a 15-year hike. Imagine that. So there's been some strange things found over time on movements of men and animals. So here we are, guys. These are the age of the dinosaurs. Look here where we got sharks right here, the Cretaceous period. This is before that 50 million year old, that warming period 50 million years ago, my friends. Sharks survived it, unlike the articles today that suggest they can't do it. Oh, the babies can't possibly survive the warm weather. Oh, come on. With feathered birds shut up here, feathered dinosaurs back here, they have flying insects in both of these. Plesiosaurs up here and down here. They all went. So look, it looks like the creatures kept getting more complex as it went forward. Early mammals, or mammal-like reptiles, were here. Here's the early mammals. And feathered dinosaurs. Here we've got feathered birds. Plants change a lot. See, ginkgo-like trees, ferns, but now we had conifers, which we know today. Flowering plants started showing huge expansion of flowering plants. Okay, there we go. So there we are, my friends. What's the driving functions? Well, just like when the magnetic field dips, or when the solar strength dips, or hopefully not both at the same time, but maybe both at the same time, you're going to get more galactic cosmic rays, or maybe other things that give you more galactic cosmic rays. More galactic cosmic rays do seem to be tied into things getting cooler for some reason. And the article that we covered that in certainly doesn't rule it out. And they think that there's other mechanisms. When they check for, they're claiming is insufficient to do it, at least by itself. But in conjunction with other things, it may be still an additive piece of the puzzle. Because quite often the puzzle takes several pieces to put together. Not many puzzles exist on the merits of just one piece thereof, right? Okay, we're going to stop that share. Hey, hello. Hang a rocket from a balloon, and off we go. We're going to go to a balloon. We're going to go to a balloon way out in space. We're going to begin space colonization race. Here we are. Did I share that? No, I didn't share it yet. Here we go. This is my ASV5, Allison Sphere version 5. Yeah, I got some steps up to this. So this is a bubble, kind of like a balloon, high pressure bubble at 14.7 really PSI inside. It would be a mile across. floating in the atmosphere of Venus. It's going to get so cold on Earth, we might have to go to Venus. Oh, I didn't show you something. We're going to go back to the Ice Age a minute. This is the kind of home I'm talking about. You can live in and grow all your stuff in. This is like a basement underneath. It's got a growing area that's completely enclosed. So this has got a layer all the way underneath here. This could be opened all the way down to that bottom courtyard, though. You so chose. Living area going on the roof. Just here on the top, you got 1/10 of an acre, which is I call the DeVase unit, because that's enough food to feed the DeVase family, and they've also make a living selling from 1/10 of an acre. This is edge on view of it. My cursor don't quit on me. Sometimes it does. That's my floor pan. This is my friend's floor pan who's detailing this out for me. Afi Beji. Hope I didn't murder her name. She is from Tunis, Tunisia. And she's doing a lot of work on this for me right now. A lot of good work. I got better drawing of that now. I should show you again. That's back in here. This is inside, showing a lot of plants growing. Guys, there's ways. I'm developing this. This is what I want to look like inside. This is what we're working toward right here. All right, I'm gonna get out of this. I showed this more in my last video. It's not the purpose of this video. I want to go back to the other because I wanted to show you something about ice ages. So one thing I really missed that you want to see about the ice ages. Over time, they say the sun, as it starts fusing heavier elements, will get hotter and hotter. It's continuing to get hotter. And some people think that life on Earth will be impossible in just 500 million years. 500 years ago was the Cambrian explosion, when we had the last, when we had a huge explosion of multicellular organisms on Earth, according to some people. Where it is? What I'm hunting here. On my little chip cycles. Bing. Coordinate. That's where I wanted to be. I thought that was here. Yeah, here we go. Oh yeah, we're all here. We are. CO2's at 300, almost 380 parts per million. Wow! Don't tell the dinosaurs about that. They think, God, we're gonna freeze to death. We'll go extinct. Don't take us to this world. We'll be extinct. We can't handle that. Yeah, they didn't, did they? So let's get out of that. What I really wanted to show you was this chart. Dun, 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 dun. This is over the last 500, almost 600 million years. 500 million years ago, we had snowball Earth. You see this? They think the whole Earth froze over. And when it melted out, we had the Cambrian explosion. Multicellular life is mostly between here and here. There might have been a little bit back in here. But this is the Cambrian explosion period, when we came right out of this snowball Earth. And look, we've had some really warm periods. Look how warm it was. Bing, bing. This was a hot period. This is the period we call the hot period 50 million years ago. Not quite as hot as that one. About that, not quite as hot as that one. The overall heat over here was more. This is when the dinosaurs were king. All through here to right about 65 million years ago, which has been right about here. Boing. So dinosaurs are thriving over here in this hot weather. And something happened. This is our 50 million year ago hot period. Okay. If you go straight up 50 million years ago, that's the one we're talking about. It's been that real horrible hot period that had alligators in the poles. Oh, it was so hot 50 million years ago. Well, it was coming out of a cooler period. One set off by the event that wiped out the dinosaurs, probably. But look back here. Look back here. Here. In fact, this cool period is warmer than just about everything. All this. But look, there's a trend. From here, it's like straight downhill. This is like a steep cliff falling, and then really falling. So this is, the last 2.5 million years to be like right in here. This is our glaciation period. This is finally dropped cold enough to get us into glaciation period. So that's cold enough for glaciation period. I don't know what we had glaciers here. That's funny. So this is short-term average temperature, long-term average temperature. I guess this broke glaciers. I think glaciers had to warm up to melt them off. But glaciation here. So, but that's not as deep and it's not quite as cold. But look here where we're going. This is beginning to look like this. Is the Earth about to freeze over? Are we going for snowball Earth again? Yikes. Wow, guys, look at that. Just got down, 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 down. And we're worried about a little blip. A little blip in this. And this is going to end the world. Anybody look over here? Here, here, here. All this over here. Where's this? Where are we? All right, where are we compared to all that? How far back do you got to go to find any area and time that was cooler? Boom! Snowball Earth. Yikes! Snowball Earth. And it looks like we might be dropping right into snowball Earth if we're not careful. So how worried are you really about global warming? Just answer me. So, all right, we've gone long in this video. We've gone really, really long. I've been on this video now for, well, it's not an hour. Not an hour. Check that out though, guys. Yeah, the whole trend line. So we're all worried about that 50 million year ago warming period. Oh yeah. And we're about to wipe out the sharks right here because it's so warm. We've not seen this kind of warm weather. Let's say sharks existed all the way back in here. Sharks existed right here, but because we've got a little blip here, we're about to wipe out something that existed here, right? No, seriously, I just show guys. I mean, they're putting out all kind of articles left and right. All these journalists and scientists, all these scientists. 90% of all scientists totally agree with them that fund them. The sources from which their money comes. They're funded. They got a fat finger on the scale all too often, my friends. All too often. So there we are. This is the science right here. This is the evidence of what has gone before us and where we're at relative to all that. So when you hear all these people talking, we've never been warmer, blah, blah, blah. What they're doing is they're coming here and they're looking like from right here to here. You know, they're looking, you know, at their, they start their charts right here in the little ice age and go forward. They don't even look back to here. They don't even look back to here. But this is cold. This is all a cold period. This interglacial is cold compared to what went before. So they're going from the little ice age and projecting, oh my God, it's the end of the world. Look, we're not as warm as that. We're not as warm as that. And that's not as warm as that. And none of this compares to what went on during the this period. Guys, all of that is still down around here. Look at this. Yeah, guys, look at that. Look at that. So go figure that out, my friends. That's the chart. Hi-ho, the dairy-o, the snowball Earth we go, the snowball Earth we go, to the snowball Earth we go. Hi-ho, the dairy-o, cow's gonna freeze. All right, my friends, stop the share. Snowball cows, snowball milk. Hey, I got a glow ball. That's my snowball. See there? And my X-Prize shirt. My cat tore it today, though, unfortunately. Just looked a few minutes ago before I started this video. All right, my friends. So, I don't know if you watch this video this long. Just tell me. Say, Greg, I'm worried global warming scares me more than anything. Or say, Greg, global warming, give me a break. I'm worried about global cooling. Or say, Greg, I don't know. I'm still watching. It's okay to still be watching, friends. There's a lot of stuff out there. What I'm here to tell you is you better keep your eyes wide open and head on a swivel. And that's what I bring you all this stuff for, is help you keep your eyes wide open and head on a swivel. For holy smoke, it's coming at us from every direction right now. We got to get ready. That's why I tell you to prepare. That's why I cover this stuff, so that you do get prepared. But I really think this habitat I'm working on is going to be a huge answer in the future. The increase in thermal mass, dirt overhead, it'll protect you from UV, from radiation, all kind of stuff. You can grow your food out of it, all, you know, just about everything you eat. grow your food out of it, make a living out of it. Bada bing, bada bang. It's going to be awesome. And it's going to be coming to you soon because I'm going to develop it. That is my goal. So, ladies and gentlemen, with all that said, hang in there. I've got hope for the future because we're going to do something about all this. So with that, I'm going to say thank you for watching.